Alright guys, so in this first video, what we're going to do is learn about a new technique called synthetic substitution that can be a really quick and easy way to evaluate functions. So this first part is just going to set up our theorem and then we're going to use it. So we've got a polynomial to look at right here. We want to divide it by x minus 3, so we can use synthetic substitution to do that. So remember, we take the coefficients and we write them in order. So we take negative 3 off the x squared, 5 off the x, and then 4 is the constant. And then you put, for x minus 3, you would put positive 3 in a little box over here. You always take the opposite of what you see. So we bring down this first term, the negative 3, and then we start this process of multiplying and adding. So we multiply these two numbers together. 3 times negative 3 gives us negative 9, and then we add this column, and that gives us negative 4. And then we do it again. 3 times negative 4 gives us negative 12, and then we add this column, we get negative 8s. All right, so what we got when we divided that out, we end up with negative 3x minus 4, and then there's a remainder of negative 8 over our polynomial divisor. All right, so when we did that, we came up with a remainder of negative 8. This next line, it says compare the remainder that we came up with to f of 3. And remember what f of 3 is we take 3 and plug it into the equation. So we are going to calculate f of 3. So we're going to plug 3 into this equation. Negative 3 times, so I'm plugging 3 in for x right here, and then I'm going to plug in 3 for x right here, and we're just going to simplify that down. So 3 squared, we do that part first according to order of operations. 3 squared is 9 times negative 3 would be negative 27, plus this gives us 15, and then this gives us 4. So negative 27 plus 15, that's negative 12, plus 4 would be negative 8. So it is absolutely no coincidence at all that my remainder in this first problem was negative 8, and then when I plugged in 3, I came up with negative 8. That is not a coincidence. That will happen every single time. So that actually leads me to something called the remainder theorem. So the remainder theorem tells us that the remainder that I get ends up being the same as when I plug this in. So I'm going to write it kind of in symbols, the fancy way, and then we'll explain it. So we can say, if a polynomial p of x is divided by x minus r, okay, so here's what we get. So our dividend, p of x, that'd be like this right here, ends up equal to the quotient, and that'd be this, not that we really care what that is, times x minus r, and then plus, and the remainder turns out to be whatever I get when I plug r into the polynomial. Okay, so this is the important part of my theorem right here. It says that the remainder is what I get when I plug r into the polynomial. Okay, so if we kind of put it in words, what it says is that my remainder equals the number we get when plugging, we'll just call it r, into the polynomial p. All right, so if we're trying to find f of 6, what we can do is set up synthetic substitution, which looks something like this. Okay, so f of 3 ends up being the same exact thing as doing synthetic division with a 3 in the box. So f of 6 would be doing synthetic division with a 6 in the box. So finding f of 6 is the same as the remainder when I divide by x minus 6. That's what I'm doing right here. So I can line up all my coefficients. I have a 2 on the x to the 4th. There's no x cubed, so remember you'd always line it up with a 0. I have a negative 5 on the x squared, 8 attached to the x, and then a negative 7 is my constant. So we just run through the steps of synthetic substitution. So I bring my 2 down, and then I do the multiplying and adding. So 6 times 2 is 12. Add this column, I get 12. 6 times 12 is 72. Add this column, I get 67. 6 times 7 is 360 plus 42, so that is 402. Add this together, I get 410. 6 times 410 would be 2400 plus 60. So 2460, and combine those up, I get 2453. All right, so I am working with some semi-big numbers here. All right, but my remainder is 2453, so that means f of 6 is 2453. And you can tell just by how big this number is, it would not have been any fun to try to plug the 6 in here. If I plugged the 6 in here, I'd have to raise the 6 to the 4th power, multiply it by 2, square the 6, multiply it by 5, combine all these up, when this is a relatively straightforward process. I don't have to deal with trying to plug the 6 in. I just do my synthetic division, and whatever I get for the remainder, that is f of 6. Okay, so we're going to do one quick little story problem type. So it's got college students who study abroad is given by this function right here. All right, so x is the number of years since 1993, and then S is the number of students in thousands. How many U.S. college students will study abroad in 2011? All right, so that's the number of years since 1993. So when we speak of 2011, that's the number of years since 2011. I'm sorry, since 1993. So it's been 11 years since 2000, which means it's been 11 plus 7 years since 1993. So X is 18 years. All right, so what we're going to do is we want to find S of 18. So again, just like we did up here, we're not going to plug the 18 in here. We're going to do synthetic division by putting the little 18 in the box. So put 18 in the box, line up all your coefficients. So we have a 0.02 in front of the x to the 4th, negative 0.52 x cubed, 4.03x squared, 0.09x, and then positive 77.54. Okay, so we do the steps. You might want to use a calculator just to see exactly what numbers we get from all of these. So I will show you what I'm doing here. So I'm going to multiply 0.02 by 18. So I know 2 times 18 is 36, and then I have 2 decimal places, so I put 2 decimal places on here. All right, so like I said, a lot of these calculations you're probably just going to want to do in a calculator. So you can do, something like this, like negative 0.52 plus 36, and we get negative 0.16. And then multiply negative 0.16 times 18. We get negative 2.88. Combine this column up. 1.15. Multiply that by 18. So just times 18. 20.7. That one I can do. 20.79. Multiply that by 18. We get 372.6, and then I can just add those 2 columns together. So take that plus 77.54. Okay, so my remainder is 450.14, so that's what I would get if I plug the 18 in. All right, so remember this says in thousands, so my number is 450,140 students. All right, so in our previous video, we learned about something called the remainder theorem, and that basically tells you if you want to plug a certain number into a function, you can just do synthetic division and you'll come up with the same thing. Whatever your remainder is, that's what you would have gotten by plugging that value in. So the factor theorem is a very specific version of the polynomial theorem. It says this. It says the binomial x minus r so it could be like x plus 2 or x minus 4 or whatever. Binomial x minus 4 is a factor of p of x. Remember, p of x represents a polynomial. If, and only if, p of r equals 0. Okay, so this means kind of a couple things. X minus r is a factor of p of x if and only if p of r equals 0. So remember from the remainder theorem, if I plug r in, I should get a remainder of 0. That means if I divide x minus r out, I get a remainder of 0. That means it's a factor. Picture if you divided 3 is a factor of 9. If you divided 3 by 9, it would factor out evenly and the remainder would be 0. Okay, so this comes from the remainder theorem. This means when you divide it out, there is a remainder of 0, which should make sense. If you divide a number by something it's divisible by, there's no remainder. So if you divide a polynomial by one of its factors, there should be no remainder. So that's what this theorem says. So let's see it in action, just with one quick example here. So we want to show that x minus 3 is in fact a factor of this polynomial, then find the remaining factors. Okay, so you guys will see plenty of examples like this. So what we're going to do is we're going to do this synthetic division, divide this polynomial by this polynomial and show that there's no remainder. And that means that this is in fact a factor. So I'm going to set up my coefficients. So I have 1x cubed, 4x squared, negative 15x, negative 18. And then since this is x minus 3, remember you always put the opposite in the box. All right, so let's run through our steps. Bring the 1 down, then start the multiplying and adding. 3 times 1 is 3. Add this column, I get 7. 3 times 7 is 21. Add this column, I get 6. 3 times 6 is 18. Add this column, I get 0, which is super important. I needed to get 0 in order to show that this is a factor. If my remainder is 0, then that means x minus 3 is a factor because it divided evenly with no remainder. So, to find the remaining factors, we write this out. See what my actual leftover equation is. So remember the way you write that is you take one less degree than this one. So I have a 1x squared, positive 7x, and positive 6. All right, so this is what I get when I divide this polynomial by this polynomial. So when it says find the remaining factors, we're going to factor this down as far as we can. Okay, so I'm going to assume that this can factor down to x times x. And then we want to see what multiplies to 6 and adds to 7. And that would be positive 6 and positive 1. So these are my remaining factors. So this breaks down into 3 factors, the one they already gave us, and then these 2 that we just found.